Okay, so the next problem we are going to do is problem 36. So the problem says that you have 150 grams a copper ball. So see, the mass of the copper ball. So I'm just going to write the MCB. That is 150 grams. Contains 220 grams of water. So mass of the water is 200 grams. And then both at 20 degrees Celsius. So their initial temperature is at 20 degrees Celsius. And a very hot 300 grams copper cylinder is dropped into the water. So the mass, that's just the mass of the copper, copper cylinder that has the mass of 300 grams. It's very hot, temperature is unknown, all right, and it's dropping to the water, causing the water to boil with 5 grams turning to steam. So I'm just going to say the mass of the water with 5 grams, so MS, that goes into steam, okay? And so the final temperature of the system is 100 degrees Celsius. So the final temperature, so this is our initial temperature. The final temperature is at 100 degrees Celsius. And so you're asked to find how much energy is transferred to water as heat, and how much to the ball, and what is the original temperature of the cylinder. Okay, so this is a diagram. So let's say you have a ball, and that ball has the mass of 150 grams, and then you have the water. So there's the water inside, and it's a 200 grams. Now you bring in a hot object, a cylinder that is a 300 gram, and drop into the water as such that 5 grams of water turn into steam, and then the final temperature of this thing is 100 degrees Celsius. And you also find, based on the information, what is the temperature of the this copper cylinder, and also how much heat is absorbed by water. So you can see that there's an energy exchange. So you can consider this as an isolated system. And then there's energy that's given away, and there's some item that takes away energy. So this cylinder, this cylinder rod, gives away energy. But then, who takes away the energy? So the ball itself and also the water, takes the energy away. But then in just a way that, in such a way that everything is balanced. In other words, the net change within our system is 0. Okay. This gives away, this takes in the energy. All right. So how do we? So in that case, let's just say delta Q is equal to 0, and there are 3 items within our system. This one gives away energy, and the ball and the water takes the energy. Okay. So you can see that you can actually write in this way. This is the amount of heat that's being absorbed by water, and the amount of heat that is absorbed by the copper ball, and then the amount of heat that is being released by the copper rod, and the whole thing is equal to 0. But based on this problem, you want to find what is delta W first. Okay, so let's say the amount of energy that is absorbed by water. Water itself contains 200 grams, and it is initially at 20 degrees. When the hot object drops into water, the final temperature of the system is 100 degrees. So we know that there is a temperature change. In addition to that, we are given information that 5 grams of water turn to steam, which means that there is a phase change occurring, and with 5 grams turning to steam. So we will use MC delta T that takes care of the energy that is being absorbed by water, in addition to the mass. So this is W indicating mass of the water, specificity of the water, and then plus the steam, the mass of the steam, and then times heat of vaporization of water, because it turns to steam. So again, all this value, the specific heat and also the heat of fusion for various materials can be found in the table. Let me see which table. In the table from the OpenStat book. Okay, so let me just give you the numbers here. So the specific heat of copper is 387 joules per kilograms per Kelvin, and specific heat of water is equal to 4,186 joules per kilograms per Kelvin, and the heat of vaporization for water is 2,256, and it is in kilojoules and then per kilogram. All right, so we have everything in front of us, so we can plug into the equation and see what we get. So the mass of the water is 200 grams, so that will be 0.2. Specific heat of water is 4,886, and the change in temperature initially is at 20, the final is 100, so it's 100 minus 20. So you got that. That is the amount of energy that is absorbed by water to change in changing the temperature, and then plus ms times LV, 5 grams of water turned into steam. So you have 5 times 10 to the negative third to change in kilogram, and LV, your LV is 2,256, and then remember to multiply by 1,000 because this is in kilojoules. We want joules. Okay, so when you do this, you'll find that the amount of energy that is absorbed by water, the first term will give you 73673.6 joules, and the second term, when it turns into steam, that will be 11280. So when you add them together, you will get 84,953.6 joules. Now, in the problem, it asks you to turn it into calorie. So how do we change that to calorie? So this thing divided by 4.186, that will change that to calorie. So after you do the conversion, you'll get that the final answer is 20.29 kilocalories. Okay? So this pertains to the amount of energy that is being absorbed by water. And you can see that we calculate to be a positive value. And then the second part you're asked to find is how much to the ball. The ball itself will also absorb energy. So how do we calculate the amount of delta CB? That will be the mass of the ball times specific heat of ball, and then times the change in temperature. Now the ball itself does not undergo any phase change. So this is the amount of energy that is required. So we have the 0.15 changing into the kilogram, and the specific heat of copper ball is 387. So 387. And then times the change in temperature, the final temperature is 100, initial temperature is 20. So when you plug into that equations, you will get the amount of energy that is 4,644 joules. So again, divided by 4.186, you'll get that in calorie, which is 1.109 kilocalories. Okay, so just based on this, we know that this is an isolated system, that there's no heat exchange within the environment, but there's heat exchange within the other component inside the system. So we calculate this, we calculate that. There's this term that has not been taken into account. And this, when you add those three terms together, that will give you 0 because the net, heat transfer to the outside is 0. Okay, so based on this, we can actually calculate the temperature, the initial temperature of the cylindrical rod. So how about let's do that? So we have our delta. So I'm just going to use the SI unit first. So your delta W, where we calculate to be this value. So I'm going to use that. So we have 84953.6, and then plus the amount of heat that is absorbed by the copper ball, which is 4644, and then plus the the energy that's being released by the copper rod. So that will be the mass of the copper rod, and the specific heat of the copper rod, and then the change in temperature. The whole thing has to be equal to 0. Okay, so this will give you 89597.6. That's equal, and then plus the mass of the copper is 0.3, and then specific heat is 387, and then times the change in temperature. The final temperature is 100. Initial temperature we don't know. and the whole thing equals to 0. Okay, so when you move this, when you move this to the other side, this will give you 0. This will give you negative. So I'm just going to move. Okay, let me just write it here. So when you punch into a calculator to calculate this, you will get 116.1 100 minus t. And then you move this to the other side of the equation. That will be negative 89597.6. So after you do this, you'll find that your t is equal to 771.73, and then plus 100. So the final answer is that the temperature of the rod is 871.73 degrees Celsius. Okay? So this problem basically tells you that when you have an object that is initially have their own temperatures, when it comes to a thermal equilibrium, some of the heat will be released, some heat will be absorbed, but then the sum, when you add the what's lost and what's been gained, that has to be equal to 0. So because energy is conserved. Okay? So that's problem 36. Alright, so the next one I want to do is problem 43. Alright, so problem 43. I'm going to draw the diagram first, and then I'm going to read out the problem. Let's see. Alright, so problem 43. So in this diagram, a gas sample expands from V0 to 4 times the initial volume when while its pressure decreases from initial P0 to a quarter of its initial value. If this initial volume is 1 meter cube and the initial pressure is 40 Pascal, how much work is done by the gas if its pressure changes with volume via path A, path B, and path C? Alright, so basically this is your initial point and this is your final point. And you can see that it's taking 3 different routes. You'll also find how much work is done through each path. Okay? So let's find out what is initial and the final pressure. So initial is 40 and the final is 10 Pascal. And then this is the initial volume is 1 and then the final volume is 4 meter cube. Alright, so let's see how do we calculate if the path is taken from this point, initial point, going horizontally, which is keeping the pressure at the same time, and then and then going down, keeping the volume at the same. So how much work is done? So let's say WA. How do we calculate WA? Now, to calculate work, we use this expression, PdV, if the pressure is a constant. So for path A, you go for the constant pressure, so you can definitely use that equation. You just need to figure out what is the change in volume doing from this point to that point. And then from this point to that point, we know that there's no change in volume. There's no change in volume, which means that the amount of work that's done by gas will be 0. So the first part is P naught times the change in volume, and the second part is 0 because it is at constant volume, no change in volume. All right, so your P naught is 40, And then we need to multiply that by delta V. What is our delta V? From this point to that point. The final is at 4, and initial is at 1. So when you do this, you find that 40 times 3, that gives you 120 joules. So this is the amount of work that is done by gas if you go from this point through this, this upper, path. Okay. Now, let's find out how much work is done if it's taken from this point to that point. Now, if you look at this is a straight line, but its angle is angled like this. So in order to calculate the amount of work, if you use P delta V, you have to actually use integration. And in fact, if you just look at this, this is equivalent to finding the area under the curve. So what is under the curve? This is the initial point. This is the final point. So the area that's under the curve will be the trapezoid. Okay, so we have what is the formula to calculate the area under this trapezoid? Then you would just use adding this together. So this from this point to that point, that is 40, and then from this point to that point, that will be 10, and then divided by 2, and then multiplied by height. So the height is the volume difference. So that will be 4 minus 1. Okay, so what we have here is that you have 1/2 times 50 times 3. So altogether, that will be, you will get a value that is 75 joules. Okay, so this is when you have a straight line diagonal, directly like this. Then you can just find out the area that's under the curve. In fact, you can also use the same process to calculate the area under this curve. So you will get this value, okay? Because what is what? That is P delta V. That basically, when you have a PV diagram, that just tells you what is the area under the curve. All right. So for this case, because it's straight line, so you can use the formula for the trapezoid, and then it's very easy. Now let's calculate the work done by when it's taken through path C. So it's go from this point, and then go from that point. So we can see that what is the area under the curve? That will be just this part, okay? Under this and this. So that will be that. So what would that be? That will be this height is 10. Is a rectangular, and then times the this section, that will be 4 minus 1, so that will be 30 joules. Okay, so this is basically how you calculate the amount of work when this goes through different paths.